program. Johan Paulson is feeling unwell today. So what we're going to do is Dave has very kindly agreed to fill in for this session to do the last part of his tutorial. And hopefully if Johan is feeling better tomorrow morning, he's going to give his talk at 9 a.m. in here. So thanks very much, Dave.
No problem at all. So welcome back. I was planning to redo these slides tonight. I mean, to smooth them over. So we'll see. I mean, they may be a little rougher, but we'll see. So my goal, let's recap. I spent a lot of time constructing the models. Then I talked about approximation methods. So now I want to talk about some more advanced stuff. So in particular, I want to show how to use, at least in a couple instances, these representations to develop Monte Carlo methods. And the key, and I'm going to show this, again, I'm kind of going to the lowest level here. I'm going to start at the beginnings of Monte Carlo and show why variance reduction is really the key to a lot of these things. This isn't working because it's not on. How variance reduction helps you. I'll show how to then use coupling and variance reduction ideas in the setting of Monte Carlo for computing expectations, and this is going to be the multi-level Monte Carlo part. This is what Des talked about. He showed the analysis behind the MLMC algorithm. So again, that'll be a little bit repetitive, but usually seeing things twice is not a bad thing if you're actually trying to learn what these things are. And then I'll also talk about something you haven't seen yet, at least in this conference, computing efficiently sensitivity, so derivatives of expectations with respect to parameter values. As in the morning, please ask questions. I thought we did pretty well with that, so keep that going. Okay, so again, when I say I'm going to start at the beginning, I just want to start at the beginning. So Monte Carlo. Let's say I have a random variable, x, and I want to estimate its expectation. Okay, so I want the expected value of x. The reasonable way to do this is just to take an ensemble average of independent copies. I didn't say they're independent, they're independent. Independent realizations of the random variable x. So I take my average. Now I want a confidence interval of size, let's say order epsilon. So how large must n be? Well, what does this mean? For my confidence interval to be order epsilon, so I need the standard deviation of my estimator to be order epsilon, so I need the variance to be epsilon squared. So the variance, these are independent, so I can just pull out the 1 over n, that's 1 over n squared. Then I have the sum of the variances. Anyway, at the end of the day, it's 1 over n times the variance of my random variable. That has to equal epsilon squared. You can solve that. So n has to be the variance of x times epsilon to the negative 2. Yeah?
Maybe stupid, but in order to be of order epsilon, doesn't that mean that the variance should be a constant times epsilon squared? Or
yeah, sure. Yes. Take it to be epsilon, though. The constant's 1.
Okay.
Yeah.
But in principle, you have no way of knowing that it will be 1.
No, but so I'm saying if you want 10, I mean, you just redefine your epsilon then. Take it to be epsilon.
Okay.
Right? I want a confidence interval of exactly epsilon.
Okay, perfect, thank you.
I fall into these order arguments too quickly, but okay, that's the idea. Not much you can do about the epsilon to negative 2. The hope is that we can, already you can start seeing that n, right, it depends on how accurate you want. But also on the variance of your underlying random variable. So if you can get that variance down, you can simulate less paths. Okay. So let me, again, very quickly give Monte Carlo if I was estimating an SE. So basically, I just want to show something with bias, right? So typically, a lot of times you can't estimate the underlying random variable exactly. So here's a good example. You're simulating some really nice SDE. I want to estimate some expectation of a function of my SDE. So I'm going to let Z be a solution that I get from Euler-Maruyama, or whatever other method you want to use, I don't care. But let's suppose it's an order 1 method, so the difference in the expectations is order H. So what do? How do you analyze this? Well, there's the expectation I want. There's my estimator. These are independent realizations, and somehow it became capital, maybe. Or maybe I'm closer. Adding and subtracting the actual expectation for my numerical methods, you see there's 2 parts to your error. There's the bias, and then there's the statistical error. You have to get both under control. So to get the bias under control, you choose h to be order epsilon. And you choose n, just like before, to be order epsilon to the negative 2. So how much does this cost? Well, you have that many paths times h to the negative 1, because you've discretized time, so every path costs, you have order h to the negative 1 steps to create one realization. This is epsilon, that's epsilon squared, so you get, or epsilon to the negative 2, so you get epsilon to the negative 3. Okay? So that's, and Des flashed this yesterday also. The standard computational complexity for solving this problem would be order epsilon to the negative 3. Okay, how can we do better? And of course, there was a talk yesterday on multi-level Monte Carlo. I think Ruth Baker is going to give a talk on multi-level Monte Carlo. Mike Giles is here. So yes, there's ways to do better. So here's my take. Again, I'm not going to go into all the details. I'm sure Mike will do that on Friday. But here's the high-level idea. So let's suppose I want to estimate this random variable x. But let's also suppose realizations of x are expensive, or just more expensive than I'd like them to be. What can you do? Well, you can use a control variant. So let's now suppose that I can generate both x and another random variable z. Let's call it z sub l. You'll see why in a second. Let's suppose I can generate them simultaneously. Okay, so what that means is I can build them on the same probability space, so that they're coupled. Okay, so and I want to do this so that the variance is small. Okay? Why? Well, and again, you saw this yesterday. The expectation I care about is I'm just adding and subtracting the same expectation. That's all it does. So this is trivial. Right? The fact that these are under the same expectation tells me that these are being built on the same probability space. So you have to be able to generate them simultaneously. The idea is now I'm going to build two estimators, one for this, one for this. And you hope you got something out of this because you think, well, wait, the variance of the difference, I'm assuming, is very small. However very small means, right? It's small. The point is I don't need very many paths to estimate this very well, to have this be a good estimator. Okay? This guy, I might still need a lot of paths. There's nothing I can do about that. But maybe this is much quicker to generate. Okay? So I can win if this is fast to generate and this variance is sufficiently low. That's the idea. It's just basically a control variant. The idea of multi-level is you keep going. So here, I've done it once. I'm very happy with that. So now I hope that there's another process that I can simulate simultaneously with this guy. Let's call it ZL minus 1. So we do that, and I add it back on. So I've played the game twice, and now you just keep going. Dot, dot, dot. Okay? So those are the multi-levels, yeah.
Do you need or want independence of the red and blue terms?
Yes. At least the way I do it. I don't know if there's fancier ways out there. Yes, that's a very good question. I would generate these independently from that guy. Yeah. Yeah, I mean, again, my understanding of this is you want the variances to add for the different estimators. So, good question. You should hold that for Mike Giles, though. I wouldn't be surprised if there's something fancier out there now. So, okay. So again, you saw this in Des's talk, but I'll go over it again. Here's an SDE. I want to approximate this expectation to order epsilon. I let ZL be Euler-Maruyama with different resolution, with different time step resolution. So I have fine discretizations all the way down to coarse discretizations. You choose H sub L. This is your finest level to be order epsilon. So that controls the bias. So the first step is that guy, what I actually care about, needs to be within epsilon of the actual solution. Okay, so you choose your coarsest level according to the accuracy you want. And then you just do the telescoping sum idea for this random variable. There it is. And as Des mentioned last time, this often reduces the complexity from order epsilon to negative 3 to order epsilon to negative 2 times the log term. And there's, again, other, this is, should I call this vanilla MLMC? I don't know. There's other fancier ways to do this. Okay, that's MLMC without the analysis. What about the current setting? So the question then is, okay, that's great for SDE. So in SDE, sorry, maybe I should say this. You can write down the SDE, right? I have to couple ZL and ZL minus 1. That's the game. can I generate these processes simultaneously so that they stay together? The variance of the difference is small. And it's sort of natural how to do that in the setting of SDEs, right? So there's my SDE, right? I would just use the same realization of the Brownian motion, right? So when I generate the normals, I reuse the normals in the appropriate manner, and then they're coupled. I built them on the same probability space, okay? The question then becomes, in our setting of stochastic jump processes, how do you do the coupling? So, okay, let's go back to our setting. We have an exact process. Now, X of t is a chemical system, biochemical system. That's my exact process. Z sub L, again, tau leaping with step size of HL, which is, again, just think of 1 over 2 to L. It could be 1 over 3 to L. It doesn't matter. Okay, so different scaled resolutions. And we have different versions of tau leaping. That's what these are, or Euler's method. Again, sorry, I'm being redundant. This is why I wanted to smooth the slides out. Anyway, so there's MLMC in our current setting, right? So I start with the process I care about. I have my multiple levels, and eventually I get a huge telescoping sum. I have to build one estimator for this guy, one estimator for each of these guys. These are all my estimators, and another estimator for at the courses level. Now, what I want to point out, though, there is a big difference between this method and MLMC for SDE. So for this method, and again, something Des pointed out yesterday, at the finest resolution, we can actually couple, I'll show you how in a second, the exact process with tau leaping. So even though we're using an approximate method, tau leaping, at different scaled resolutions, we correct for the bias at the very finest resolution, so this becomes an unbiased estimator. Okay? So it's a nice thing. Questions? Is it all clear? It's a telescoping sum. That's all I've said. I've spent 15 minutes saying telescoping sum over and over again. Fine. Then the question is, okay, so the real question. We don't have Brownian motions. How do we do the coupling? Okay? So now you have options because you sat through an hour and a half for this morning, right? So I just have to simulate, you know, I'm only focusing on this level. I want to couple an exact with a tau leap process. Forget the tau leap stuff, okay? I know how to simulate an exact process. I can use Gillespie's algorithm, or I could use the next reaction method, right? So why not just couple these guys through, let's say, Gillespie's algorithm, through the Poisson process and those uniforms, right? Here's a representation for tau leaping using the equations for Gillespie's algorithm, right? Again, the only difference between these is this eta function that pops up in the approximate process. So you're always holding your left endpoint fixed. So, I mean, it's hard for a human to parse that real time, but this is just Gillespie's algorithm for the exact process, Gillespie's algorithm representation for tau leaping. The key point is they use the same Poisson process in the same uniforms, okay? So you can do this. It is a coupling. It is like a lot of times the first thing you would think of if you think in terms of Gillespie's algorithm, but it doesn't work at all. The coupling is not good and you don't get any benefits, okay? So I'm not going to show that. I'll show that later in the talk. So that doesn't work. So then you think, well, he seems to really like the random time change representation. So maybe we should try that one. And the most natural coupling for the random time change representation is just to use the same Poisson processes, right? The Poisson process was the driving noise or the driving randomness for these processes. So why not, you know, pull my Poisson processes out of my pocket, simulate X, use the same Poisson processes, and simulate Z using tau leaping. Okay? It's very straightforward how to do that. That doesn't work very well either. I'll show you that later on, again, when I have a simpler setting. So take my word for it now. That works okay, much better than the Gillespie representation. And I'll have a picture later showing you can just see the variance doesn't behave very well. So that's not the answer. So the answer turned out to be something different. And again, Des went through, I feel very repetitive here. Des went through a similar thought experiment, but I'm going to do it again. So what we're coming down to is we have to think about how to simulate non-homogeneous Poisson processes simultaneously. That's what it comes down to. Every reaction channel has its own Poisson process. Okay, so think about how to simulate a Poisson process with rate 15 and rate 13. From what you now know, a good way to do that would be this. I could have one process running at rate 13 and I let both processes share those jumps. They're jumping simultaneously. And I then just have an auxiliary process for this guy running at rate 2. And I guess I haven't said this. When you add Poisson processes, you get another Poisson process, and the rates just add. Okay? So this actually, as long as these are independent. So this actually is a rate 15 Poisson process. That actually is a rate 13 Poisson process, but they're sharing all these jumps. So they jump together almost every time. Just every so often, this guy will bump up the second guy. Okay? Does that make sense? Pretty straightforward. If I want a non-homogeneous Poisson process with intensity F and another one with intensity G, right? The key of what I just wrote down was 15 is a theorem here. 15 is always bigger than 13, right? So it's easy to figure out which one needed the auxiliary process. I just needed this guy, right? But if I have F and G, right, here's F, and here's G, right? Sometimes one is bigger than the other, right? And the point is, on this example, they shared 13 because that was the minimum. That was like the base level, and then you just needed an auxiliary to pop up. So what do you do if you have functions f and g? It's sort of clear, I think. You run them both at the minimum. You have one Poisson process running at the minimum. I shouldn't have used blue, of course. Anyway, right? The minimum is you're running both of them simultaneously, and then for this is g. When f is the minimum, you just have to have an auxiliary process running at the difference for g. Okay, and then you add the rates together and you get the right thing. So does that make sense? So you're simultaneously running them at the minimum, and then you just have whatever you have to do so that when you add this together, you get the right rate. Okay, is that clear? Questions? Yeah.
Does it make sense to say that one of those auxiliary processes will always be zero?
Yes, that's actually a great observation. So when you think about how to actually simulate this, it looks more complicated. It's not that bad, because exactly what you just said, one of them is zero. Either F or G, or both, are actually achieving the minimum there. And so one of these intensities is always zero, and so you just have to worry about two. You always have to worry about y1. When is that going to jump next? And then only one of y2 or y3.
Does that not mean you could just use 1 instead, 2?
How?
Like switching across.
You could thin. I mean, you could have one master process running, I guess, at the max minus the min, and then have a thinning.
When you've got one running at any time, it's got a rate of 0, so it's staying where it is.
Yeah, you could do that. You could do that.
Yeah.
That'd be the same. Yeah. Yeah.
So and just in the context of, I mean, I guess you're gonna show it later on. So maybe I'm jumping ahead. So, I mean, when it comes to the you showed this example before with the 15 equals 13 plus 2.
Yeah.
So should we think that the 15 is basically what comes from the Tau-Lip discretization, and the 13 is what comes from the...
That's fine. Yeah, or think of f and g that way. Think of f as the intensity function here.
The true intensity function.
There. Right. So there's the processes in the random time chain. But here's the coupled processes, which again look horrible, but they're not that bad. You've just taken every reaction channel and broke it into 3 pieces, just like I explained, right? So for one reaction channel, you're running them both at the min of the intensity functions, right? And you're exactly right. It's the rate is lambda of your Tau-Lip process still at your left endpoint. That's the key. And then you have your auxiliary. Here's the Tau-Lip rate minus the min, exact process minus the min. Okay?
But it's not, I mean, thinking about it intuitively, going back to what Simon asked, I would expect that only one of the two processes would have a real plus, in the sense that it would...
A what? Sorry?
A real plus. So you would simulate an extra Poisson process for only one of the two, either for X or...
Well, at any given time, one of these will be 0. Is that what you're saying?
Yes, but it's not. But I guess what I got wrong in my mind, that it's not always the same thing that is 0.
No, absolutely not. That's exactly right. So you could have the exact process below the Tau-Lip process for a while, the intensity, at which point this would be 0, and then later on it switches. Yep, absolutely. Yep, time dependent. Yeah, good questions. Okay, now any other questions? What's cool about this also is simulation's no harder than, right, if I wrote down the original random time change representation, I say just use the next reaction method. And people at least nod and say, yeah, that's what you do. This is still in the random time change representation. It looks worse, there's just more, the sums are bigger. But it's exactly the same thing. You just have sums with counting processes. It's exactly the same thing. So if you can implement the next reaction method, you can implement this. So now you've coupled these guys together. There's the coupled tau leaping. Again, it looks bad when you stare at it, but it's not that bad. It's just, again, it's tau leaping on different discretization levels. I actually don't want to get into how to actually, I don't think anyone cares about the nitty-gritty about how to actually do this, but well, I'm going to say it. I mean, just like tau leaping, you just compute Poissons along the finest time step. That's all you're doing, and you generate your process. So I'll leave it at that. Simulation, I just want to stress, is not hard. It's no harder than normal exact simulation and normal tau leaping. But then the question is, does it work? Right? So what Des showed yesterday, I want to show something Des didn't show. So what Des showed yesterday was some asymptotic results we have in a particular scaling. How does it behave as something goes to infinity, et cetera. What I decided to show instead of that, because you've already seen it, is just a model. Here's a fixed model that I want to implement multi-level Monte Carlo on, no scaling at all. This is the model. Let's just solve for something. So we're going to solve for this is a transcription, translation, then the protein dimerizes. So I want, at time 1, I want an estimation of the number of dimers with an accuracy of plus or minus 1 with a 95% confidence interval. And here's the output using multi-level Monte Carlo. The exact algorithm took 41 hours on my laptop, so I mean, this is not a supercomputer I'm using, obviously. It took a lot of paths. For unbiased multi-level Monte Carlo with different parameters, I mean, I ran it multiple times. This is just whatever the finest resolution I chose that moment was. They always gave, obviously, the right answer, and you reduce your time from like 41 hours to like 15 minutes. So it really works in practice. Just, you know, I mean, in general, MLMC is a great idea. Okay, that's MLMC. So again, you're going to see 2 more talks if you go to all the talks on MLMC this week. I don't know. Now's a good time to ask questions, though, if you have any about it. This was a quick MLMC, yeah.
Do you have a feeling for what's better to do the exact coupling at the bottom, or just keep going with the levels until you get your bias below an acceptable level?
Wait, say that again.
Do you have a feeling for what's better to do? Is it better to couple to the exact thing at the bottom, or is it better to just keep doing enough levels till you reduce your bias to?
So this is a personal bias. I like unbiased estimators. I feel better having an unbiased estimator. You absolutely, in fact, people do think differently about this, that, yeah, you can just simulate your levels deep enough until you're comfortable with the solution. That's fine, too. I just prefer unbiased. I'll just leave it at that. I don't have a good feel of I mean, the bias version, well, you know, it's funny. It's not always even quicker. You know, because you have to worry, you have to go low enough in levels that you actually get into problem areas that you actually slow down your computation. So it's not even clear. Yeah,
But sometimes, I mean, if you have a tolerance that is not very big, it's, I mean, sufficient to...
Absolutely.
Yeah.
That's exactly right. And by the way, I should mention there's a good poster right on the other side about... So I'm showing vanilla MLMC in this case. So there's a nice poster on non-vanilla MLMC where if you have a stiff problem, how do you handle that? So I recommend people go look at that. Yeah.
So going a bit back to that question, so you have step size parameters. I mean, I guess in your case you kind of made sure that 4 to the minus 5 is not big enough that you're essentially doing Gillespie or next extraction method. So you still have some computational benefit from not going all the way. So
yeah.
And I mean, okay, this is a simple example, so
yeah.
you can kind of wave hands a bit and sort of find
yeah.
what that HL is. In principle, is there some recipe for choosing HL?
So, I almost did it again. In general, I don't think there is, because there's a lot of models out there. In the classical scaling, one thing that was interesting in this latest work is there is. So if you want to do, in the classical scaling, you want to, what Des talked about, how we were doing the scaling. Maybe we can talk after. I'll tell you the answer. So, right, so the finest scale, let's say the system is order V. So the time resolution, right, is 1 over V. That's right. So your intuition may tell you 1 over V. But it turns out it's actually 1 over V log V. Turns out to be not asymptotically better, but you get a much better leading order constant. So you want to kind of push away from, right, the natural lower bound for the step size is however long it takes the exact model to make its steps, right? You should never go below that level. So the only question is, do you hit that level or do you go a little bit above it? And we found log, like take that and multiply by a log term of how big your system is, tends to do the best.
So log V divided by V.
Yes. Yeah.
Do you need your step sizes to be nested, or could they just be smaller and smaller without being half or 1/3 of each other?
So I don't think you actually need the step size, for it to be, oh my God, my brain is not working, a geometric, my brain is turned off all of a sudden. Yeah, anyway, they don't need to fall on each other, but it's much easier to implement if you actually have that. Now, but some people have done adaptive methods, and so, you know, there's other bells and whistles you can do, but so it's not necessary. I find it's very easy to do that. I mean, the idea is, in general, you're simulating, right? You want to, the coarse resolution would be to go from here to here. The fine resolution is to go from here to here. So you want to basically pick up noise here, and then easily just put it together and figure out what you did on the coarse resolution from there to there. And I find it's easier to do it when they fall on each other, but it's not necessary.
Oh, yeah. So because on the finest level where you have random
Yes.
time sets, and of course they don't fit usually.
Exactly right. So that's a great observation. So, and it doesn't matter. That's the key. So this is sort of a subtle point. When we, where is it? When we simulate tau leaping coupled with the exact process, so usually when people think of tau leaping, they think of I generate Poissons. You do not do that in this when you're simulating this representation. We actually use the next reaction method for the tau leap process, meaning we simulate every jump of the tau leap process. I don't know if that makes sense or not. Okay, so right, this representation is valid for all time. Right, the standard tau leap algorithm was you generate Poissons and you only look at your process at these discrete times. We're not doing that here. We actually look at this process at all times, but we only do it on the finest resolution. Because then once we go to the next level, Lord, right? Once we go into these levels, no longer do we actually have to look at the tau leap process at all times. We can actually just use Poissons now. I don't know if that got through.
Isn't that more? I mean, so you say that on the finest level, when you stop at HL, even for the tau leap, you sort of don't do tau leap. Is that what?
Yes. Imagine this. Take that model. Okay. Forget multi-level Monte Carlo. Take this tau leap model. Okay. All you're doing is freezing your intensity function at the left endpoint. Okay. How do you simulate that? Right. I would again write down. The standard picture I have of my Poisson point process. And it's just that, you know, my intensity doesn't change when I hit these points. Right? You can still simulate this exactly under the assumption that, well, sorry, the word exact is dangerous there. Right, so if I want to simulate a tau leap process exactly with every jump in between, I just do it. Right, my intensity at the beginning is lambda 0. I ask how long it takes me to get there. It's this gap divided by lambda 0. Normally, I would update my intensity functions. I don't do that. I just compute again with lambda 0.
But
until real time has hit time h, then I update my intensities, and then I continue on. That's what we're doing here.
So essentially, you're doing next reaction method of the sort of like numerical method somehow.
We're doing next reaction method on this representation of the
time frozen coefficients, basically.
That's right.
You only update. Okay.
Yes.
Okay.
So you freeze your coefficients for z, not for x, until real time hits h,
And then you update.
then you update, continue on. Okay? Make sense?
Yeah.
Yeah. Yeah.
But that was just for the finest level now.
That's just for the finest level. Okay, so so we're really getting into this. So this is good. So once I mean, you have to do that on the finest level because you're looking at the exact process anyways. It costs you nothing, right? At the finest level, you're simulating x, so you may as well simulate z exactly. Costs you nothing. But once you simulate coupled tau leaping process, right? Here it is. These are fixed, always fixed, right? Let me go back. I'm really not wording this well. When you're coupling x and z, whenever there's a jump, you have to update x anyways, the intensities for x. So you have to look at everything. But for z, nothing gets up, when you're coupling the z's, nothing gets updated from one time step on the fine resolution to another time on the fine resolution. So you can just generate a Poisson and another Poisson and be done with it. And you just jump over it.
So if you were to write the code here, it would just be tau, like you choose your h, and it would just be h times the Poisson.
It'd be h times whatever this number is, a Poisson random variable for that reaction channel, h times this random variable, a Poisson with that parameter, could be 0, one of them will be 0, h times this, add them up, repeat process. But that's all in the fine resolution. And then you'd update the fine process, you'd have to do 2 jumps for the coarse resolution, then update the coarse resolution, etc. Wow, that was nitty gritty. Okay. It's not hard. That's what I want to say. It's no different from actual tau leaping once you sit down and think about it a little bit. Other questions about that? That seems to actually work. Okay. Well, I'm almost out of time. When do I finish? Quarter past? I'll say, just a few minutes. No more questions about MLMC? Okay, a different problem, which I don't think anyone's talking about here, so this is a good time as any. So let's imagine you're computing, I have well, this is what Darren was talking about to a point. So I have a parameterized family of models. So I'm parameterizing by theta. So these are my rate constants, okay? And I want the derivative of some expectation with respect to theta. Okay? That's what I want, this. And it's useful for control, blah, blah, blah. It's useful in lots of applications. So let's just take that for granted. So there's multiple ways, let me stress, there are multiple ways to compute these derivatives. Okay, I'm going to show one because it fits nicely in with what I showed you this morning. Okay, so it makes a more coherent story. But there's likelihood methods I'm not going to show you, etc. So if you're interested in this, you want to hear more about it, please come and talk to me. But let me just show a very basic idea, which should be very obvious to you right away in terms of finite differences. So how can we estimate this guy really quickly and efficiently? So what's a finite difference? This is exactly what it sounds like. If I want a derivative, let's do one-dimensional. I take a finite difference, and this is just, 2 expectations, the difference of expectations. The problem is I have this epsilon. Oh, man. This epsilon doesn't mean what it did 5 minutes ago. That's always trouble. I merged 2 talks, as you can see. Okay. Anyway, so this has a bias of order epsilon. You can get the bias out if you do some center differencing. That's trivial. The real trick is getting the variance down. So there's your finite difference estimator. And you can just do the computation. So the variance of your estimator is, you still, right, I have r paths now, so I still get a 1 over r. I still get the epsilon -2 comes from the perturbation. And then I still have the variance of my numerator, of my random variable in the numerator. So when you look at this, this is pretty bad. We picked up an epsilon to the -2 because of the perturbation, and so it can be really beneficial. Then the goal is going to be to get the variance of the difference lower. If we can get that variance down, then hopefully we can control for some of this, because this really is bad news. That's really bad that I'm reusing epsilon, but anyway. Okay, so I'll skip this. I mean, it's helpful, the variance of the difference, you get a covariance term. I think this is pretty clear now. So coupling can reduce that variance. So the question again is, how do you do the coupling? And honestly, it's like literally exactly the same as my MLMC little spiel a second ago, right? You could use what's called common random numbers. This is very common in the literature. In common random numbers means you use the same random variables as you did in Gillespie's algorithm. So that means you're simulating this representation. I have one process with parameters theta plus epsilon, one process with theta, and you simulate using the same uniforms and same Poisson processes. It's very simple to do this. To do this, you just use the same seed for your random number generator. That's it. There's no upfront cost whatsoever, okay? And it works reasonably well. So it costs nothing in terms of implementation. You can really get huge gains in variance reduction. The interesting thing, though, is often this coupling doesn't work for the long time, and they decouple completely, which is not obvious that would happen. And can we do better? And again, I'm just going to splash it. It's the same coupling you just saw for MLMC. I mean, why try anything else? Oh, sorry, that wedge means min. So it's just the minimum of the intensity functions and then the difference. Same coupling, use the next reaction method, you're done. You can prove theorems. I won't go through it. I mean, you can prove that it actually lowers the variance an order of magnitude. But this is the kind of proof is in the pudding thing. So here's just a very basic model, but take my word for it, this comes up over and over again for much more complicated models. If you just do straight up Monte Carlo, you see that pretty quickly the variance of your estimator converges to something around 400. Don't worry about that. That's the likelihood method that grows and grows and grows. If I just reused, a different coupling, if I just reuse the Poisson processes, that works okay for a while, but eventually that fully decouples. Okay, so again, what I'm saying is if I just reuse the Poisson processes for my counting processes, that again works for a while, but then completely decouples over time. Common random numbers, so Gillespie using the same seed, again, completely decouples over time. And what I mean by that is, the variance of my random variables converges to what the variance would be if I just simulated them independently. Okay? Whereas this stronger coupling, CFD, converges to something, but it converges to the number 1 thereabouts. So it's about 400 times more efficient. The variance is 400 times lower. So it really works, and it ends up, saving you huge amounts of computational time. Here's another example, the Schlogel model, I think, some genetic toggle switch. Again, same story. If you couple using common random numbers, the variance grows and grows and grows and grows. Whereas if you couple tighter with this other representation, your variance grows and then plateaus at a very, very low number. So to me, this is sort of the take-home method, right? This is the goal of why the heck you may want to sit through a tutorial that takes 3 hours of how to develop these mathematical representations for the same model, right? I mean, that seems crazy when you say it out loud. But this is why. Because when you're presented with a specific problem, in one setting, using one mathematical representation may be beneficial. In another setting, using a different mathematical representation for the same model may be beneficial, also, right? So, and this is the proof, like using the next reaction method with the random time change representation, you can cook up something with a ridiculously good variance, with good variance properties. Whereas if you just do common, reset the seeds of the random number generator, not so good. Okay, recap, I'm not gonna do it. So there's the references. Again, I feel a little bad. There's a million, I've talked about 1 million papers, and I left out 1 million papers. I've shown the vanilla version of everything. So I can't fit everything, so I fit almost nothing. I think it's worth referencing Dan Gillespie's first few papers. Gibson and Bruck cooked up the next reaction method, but not using the random time change representation. That's mainly Tom Kurtz. And then we have, again, some survey. I'll say, if you're looking for survey articles, this is a good survey article. This 80-page book or monograph, that's more for if you've taken a graduate level probability course and you really want to see the guts of what's behind all this. That's where to go. Otherwise, the survey paper will get the job done. So that's it. Any questions? Look, he hasn't, yeah.
Sorry, I did not understand why you have this decoupling phenomena for when you use
Common random numbers?
Yeah.
Or which one?
Yeah.
So this is just a fantastic question. So it's easiest to see. This is a great question. So it's easiest. Let me explain it for you. you could reuse the Poisson processes, right, for the different processes, or you could do this fancier coupling where you talk about the minimum and all that kind of stuff. Okay, so let me explain the difference between those. That's easier to explain real time. Then if you want more, we can do more. So if you just reuse the Poisson process, this picture should get it across. Okay. I'm reusing the same Poisson process, but for processes with different intensity functions. So the integral of that intensity, right, where you are in terms of the Poisson process, for this guy, I could have integrated his intensity function up to here. This guy, for some reason, I've integrated and the intensity is way out here in the Poisson process. Now, the state of the process, the state of the system, they may have touched again, right? X could be equal to z, but these integrals are still different, which means they're exploring different parts of the Poisson process. So they're actually uncoupled, well, not uncoupled, but they're not very well coupled. You'd expect that the jump times of these models would be different. Now, what's happening if they're sharing the minimum idea? With this minimum, if the processes ever touch, if they recouple, like X and Z ever come back together, then they've actually fully recoupled, right? You never get this phenomenon because the minimum is still whatever the minimum is. I'm not explaining that well. Right, so when you start these processes, if they ever touch, you have, let's say, y1, y2, and y3. So this guy's running at the minimum. So the intensity function that they're both running, they're running at the minimum. So they're at the same point for this Poisson process. So the next jump, according to this guy, they're both going to share. They've really recoupled. And these guys will be running at low intensities. Did that explain it?
Yeah, so when you use it for the common random variables,
Yes.
you said that we have bad results at the end because we have decoupled phenomena.
Yes.
So why this is happening?
Why for the common random numbers? Okay. I don't have that story as real time as I have this story.
Isn't it still going to be sort of this secular buildup of errors? I think that this merging Poisson point process is somehow permanently wiring together some relationship between the processes. Everything else is relying on the integrals being.
No, I think, so that is the story. Yes, you're right. So let's say they've run for a while, and the two processes have we're lucky, have come back together. No, I don't have that story at my fingertips. Let's talk over coffee. It won't be hard to figure out once we write it down. I just can't think of it right now. Yeah.
Two questions. So the one relates a bit to that. So you said, my intuition would say that the smaller you make epsilon, the longer time it takes for things to diverge. Is that true or not?
The smaller you make epsilon, yes, that's true.
So
yeah, but there's a trade-off. Let me just show. The variance, you get this epsilon to the -2. That epsilon, you can't get rid of that. That gives you an epsilon to the -2. Okay.
So you don't really want to make epsilon.
Exactly.
But is there sort of again, that's not the best way of doing it, but if you had some estimate of how much they diverge by time t as a function of epsilon, then maybe you could do something with that.
Say that again. If you.
So you just described very nicely how the things diverge.
Yeah.
This kind of really depends on the value of epsilon.
Yes.
The time.
Yes.
But by which.
And you're asking how long the divergence time is as a function of epsilon. I have no idea.
You have no idea. Okay.
Yeah.
And then the second.
That's a good question.
The second question, which I guess perhaps relates a bit with the things that Radek was discussing yesterday. So you do things for finite time, and you sort of say that if we do the couple clever enough, things are working. Do you have any results for what happens as time t go to infinity?
Nope. And I'd love to.
In the sense of sort of doing some bifurcation analysis of the invariant measure or something like that?
Nope.
Okay.
Yep. The answer is no.
Okay.
Yeah, but I think that's a great area to look into. There's an open problem. I'll end my tutorial with an open problem. Yeah. Okay. Other questions? Okay.